Okay. 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 Good day, everyone. Um, so today we'll continue from where we stopped and the attention mechanism. We'll run some code to, or we'll go through some code that will help us like understand the attention mechanism, the GPT architecture too. Right. So let me share my screen, or should I wait for some minutes for people to join? Let's wait for people to join in. If my screen is visible. My screen is visible. It is. So let's go on from
Your
what we
screen
have
is
for today.
visible.
Yeah, all right. And so we continue from where we stopped about the attention and what's going on in this block here. My mouse is showing. So we talked about how they're all matrices and they are doing some matrix multiplications and some scaling and then softmax and another modeling multiplication with the values, and we explain what all of this means. And after some time, we said that using just vectors was not optimizable or was not optimized. So instead of looping through vectors, we just concatenate all of them into a matrix and do matrix multiplication. Like I said, um, classic dot product is the same thing as matrix multiplication because they are multiplications of vectors, just that one is transposed and another is not transposed. So um, then we also I think this is where we stopped where I don't know why my slide wasn't showing then. Okay, to show now. Okay. So saying that actually those queries, keys and values are gotten from the X embeddings, that means the inputs, right? The embeddings of the input words or the input tokens. And actually to get those QKV, there's a matrix that is multiplied with those X's. So what's happened is that we learn this matrix W, which is Q, matrix K, and matrix V, right? And so what happens is that here the X matrices are now multiplied with the weights of each of those key query values, right? So and we get the QKVs for each of them. This, if you look at it, this is actually going to speed up all of the multiplication that need to be done if you concatenate all the vectors into matrices and just do multiplication. So what this means is that um, we are learning we are learning some embeddings or some weights, right? That will help us like know what are we like now for the values, because we said that the values are constant, is like telling you what part of the values are we to, what part of the sentence are we to concentrate on, stuff like that. So the these images will help us like in all of the subspaces, what is important, what part of this Q is important, what part of this K is important, and this V is important, right? So it's not important, what part of them should we attend to? Remember, Q is just a single value, K and V are the sentences too. So yeah, let's continue. So we can now see that this K dot product attention is just one part of this multi-head attention. And this multi-head attention, like he said, there are multiple heads. So they are like, depending on the number of heads you choose, there are like 6 of them, right? And of those 6, there are now like 12 layers of each of these blocks. So we see, like I said, the whole calculations and mathematics is quite long. And this is just like explain everything in matrix form and how the attention head, the multi-head attention comes into play is that So we now like have this Q naught, K naught, V naught, Q1, K1, V1, and all to the number of heads. Then we have this width matrix 0, the width matrix 1. So all of those are then concatenated together, right? And we have these tension heads for each of those um, vectors. So do you see that all of these Z0, Z1, Z2s, they are all concatenated together, right, to form one whole matrix W0. So that's the matrix that is used to do most of all of the multiplications and most of all of the matrix multiplications that we see. So what this helps us do is that it allows the model to like gently attend to different parts or to be different information from different representations. Right? So like in a particular sentence, there are some things that are important at a particular time, and some things that are not important. It might not just be one thing you need to attend to. There are a lot of things to attend to. So multi-head attention helps us to do all of that. So right now we'll be going to so right now we'll be going into the code, right? So I have like the notebook ready. So I'll just be going through all of what's in the notebook, right? I won't really be running all of them because that will take some time to run all of those codes. So I'll just run us through, give us some background and in your own time, because I will share this notebook with Samoye and you, it will be useful for like you in the future. So right now, what we're going to do is to look at unsupervised pre-training of GPT style model. So like as if you remember, you understand what unsupervised learning is. There's no training data, there's no Y value, there's no Y label, right? And pre-training. So pre-training means that you are giving this model a pre-training task, maybe masking or next sentence prediction, which other method that you can think of, right? So that's what pre-training is. What pre-training does is it gives this model like a basic understanding of language, like what language is. But in the meantime, training all of those weights, right? Those weights, all those matrices that you saw there. There's a whole lot of matrices going there. So yeah, one material like I'll refer everyone to is Andre Kapati. Andre Kapati is a pioneer in AI field, just like Andrew NG. Andrew Kapati has a tutorial video where he taught how to build your own GPT from scratch, and you see it has 4.1 million views. I will encourage you all to watch that, and also how he built a GPT tokenizer, which will explain somehow here. And he also like in his short videos of very, very incredible information, he shares how to do back propagation, how to build micrograd. He also built Make More, like the network language model. He just he just like explains everything I'm explaining, or I'm just like cruising through right now because of time. So your weekend, if you're not too busy, just check these videos out. I'll share it also in the chat for you. Yeah. All right. So let's go. So we're building on top what Kapati has done, what Andre Kapati has done in this code. So he built its own base model called NanoGPT. Is a repo. You can check it out also to see. And so we're going to use some of what he had done there to build upon. So you can always go through that to see what I'm talking about. So we're scrolling through now. So what we're trying to do here is have these, remember these from the slides, we have the embeddings, we have the position encoding, then they're added together. Then there's the attention, causal attention, there's the normalization, there's the feed-forward network, then there's another normalization, then some prediction. All right, so looking through all of that. So the first thing before we get there is to have our data. Please, I hope I'm still audible. Maybe my network might not be that good, but it's audible. So today we're going to work with the
Yes,
toy
you're
data
very
set called,
audible.
all right, we're going to work with the toy data set called Tiny Shakespeare, and you can um use your own data if you want to, and you can always extend this example with whatever data set you have. Like I said, the more data right, the better. But also, the more data means the more time and the more like GPU instances and resources you need. So we clone NanoGPT, install the required modules or dependencies we need. Um, okay, so then we set the link for Shakespeare. We download it using a request package. We have all of that in our file. Then we go into tokenization. Okay, when you have data in text form, remember when I was talking about data in text form, computers don't really understand those that, so you have to convert them to numbers. So before you actually even get to the embeddings, right, there is a tokenization. So the text is split up, right? It's split up, then from this splitting, you get some numbers. The next numbers are now used to do a lookup in the embedding matrix. I will most likely explain that soon. So what is tokenization is, so um tokenization is just like I've already explained, you're breaking up those long text into shorter ones. Right? There's something called the byte pair encoding BPE tokenizer. What that does is that it is used to create common words, right? So something like having an ing in front, appearing. So appearing, you don't need it. It has what it to do is that instead of having an unknown UNK token or stuff like that, what it does is that it finds a way to split up appearing to appear then ing. Then we know that there will be a lot of repetitions of ing and repetitions of appear. So it is in order to find common words, we need to find words. So what we do now is for our specific data, which are very, very tiny Shakespeare data, we're going to train a tokenizer, right? That tokenizer will help us do the tokenization of the sentences these sequences that we're going to use. And it's explained here. You can always look at it. Remember, there's a beginning of sentence token, there's end of sentence token, there's a padding, there's an end token, masking. Right, so we're going to set a target vocabulary of 50,000 tokens, and we're going to train using the Hugging Face. That's why I'm very scared about coding. Even though I've not introduced the Hugging Face library, I'm now jumping into that in first place. So sorry about that. You will learn very well about the Hugging Face library in the second stage, right? Second stage or the third stage, you get to know about the Hugging Face and Transformer libraries, right? So we train our tokenizer, then we use it, right? We use the tokenizer, and we're going to now look at an input sentence. Hack, my name be Romeo. I am but a beautiful summer's day. So this looks so Shakespearean. And to do all of that tokenization, you load your tokenizers because we have saved our tokenizer after training. We save it, right? And we load it, right, from pre-train. Then we use it to tokenize some input sentences. I hope this doesn't look complicated, right? It's just basic Hugging Faces. You can always check out the documentation too if you are very not familiar with what all of this is. So now we see how it is split up. There's hack, there is mine. This is an unknown character for some reason. So bear with that. But you see that there's my name be Romeo, exclamation, I am but a beautiful summer. You see that the apostrophe S is split into two as apostrophe S and summer. So for you to create all of this, you need to find similar words and assign them numbers, right? So then we convert those, going to assign these things IDs, right? So there's a way the tokenizer knows how to assign numbers to each of these words. So we see hack is 112077 and apostrophe exclamation is this. I think the comma is 9. So you see how it is. Okay, if you see five is exclamation here, and 5 is exclamation here. So you see that it converts each of these tokens to numbers, and that is how we are going to get the embeddings from there. So we can also get back the text from the numbers too by using the tokenizer decode method, and to help us do all of the re-tokenization back. So now that we've trained our tokenizer, what we need to do is to now create our data sets, right? We encode our training and validation data set and save them in binary file for later. So remember, we've loaded our training data from here. Where's that? I'm sorry about that. Yeah, so we loaded our training data and we have saved them, right? And what we now need to do is encode them just the same way we encoded these ones here. After encoding them, right, we find number of tokens that we have, right? And we have 291,000 tokens. Just typical, somewhat machine learning stuff. Training is more than your validation, right? So you are not overfitting and stuff like that. So um, we get the IDs and we look through the IDs for the first 100 tokens, and um, that's it. So now we go into the model part. Remember, before it gets into the model, your text are converted to tokens. There's going to be split into smaller subwords. Those subwords are converted to tokens, and those tokens are now used to get the embeddings. So let's go on with that. So now remember we cloned the NanoGPT library from Kapati, and so now we're going to be setting out some hyperparameters like the output directory for our checkpoint, because when we are training, you want to be saving the stages for each iteration. Just typical how you, let me just say simple, like XGBoost when you save each, or PyTorch or TensorFlow where you save each checkpoint as you train. So immediately the training stops. Maybe you have a a callback that stops when you're overfitting. So when you stop when you're overfitting, it just loads the recent checkpoint for you, the one with the highest validation. So we are starting from scratch. We're training from scratch. Even though we're not training from scratch today, you can do that in your own time. So we're going to set some values, evaluation interval, iterations, right? Save checkpoints, evaluation only, some flags, right? We are setting our data sets. We are setting some typical parameters for the batch, like the batch size, the block size, right? This is most likely the embedding size because it has to continue. Um, so we now set the model architecture, number of layers. This is just a small model, right? So we're saving. This is for GPT-2, the 6 layers was a small. So the number of heads also is small, and the number of the embedding layer is 516. You have a dropout. I hope you remember what the dropout is. If you did the neural networks class, dropout is for regularization. It prevents overfitting in the neural network. So we also not use the bias in the linear layers. If you remember, a linear layer has a weight W. If you remember the equation, weight times X plus B. So B, when you say B is equals to false, we are not using the B, we are just using the weights, right? There's no need for the B, right? If you remember linear regression too, you should know what the bias is. So one thing is that your embedding should be clean divided by your number of heads. So we have 516 for the embedding layer, and we have 6 heads. So that's divisible. Why? Because for the number of heads, instead of doing 516 by 516 by 516 times 6, we split the 516 into 6, right? So it is optimized, right? So you don't need is not too much like ways to save, and also it's not going to take much of your time, and it's also like learning a lot. It's going to attend, the attention doesn't stop even if you split it up into 6 heads. So remember what the number of heads are for. They are usually for multi-head attention, which is for attending to different things at the same time, right? So we have our hyperparameters for optimization. Remember the learning rates. This will most likely be for Adam optimizer. If you have looked into maybe this optimizer, you know what most of these parameters are for. These are typical values that you might not have seen if you not do the hidden implementation on your own. Maybe something like TensorFlow. These are the defaults. Right? These are the defaults, but right now we're setting them just explicitly here. There's a gradient clipping, right? Just to prevent exploding gradients. These are all typical things that are most likely done for you when you use a higher level libraries like Keras. I know some of you are very, very familiar with Keras. So all of these also are for your hardware, like NCCL, CUDA, Float 16, or B Float 16, or Float 16, Float 32, whatever. This is most likely hardware settings that I'm not going to go into right now. So you can always read up on them, but I don't think you really need to know most of these. And so now we're going to be loading our data. Remember, we set a batch size. Where's that here? Yeah, we set a batch size. So we're going to be loading data batch by batch, just like normal training, just like how we do normal training, in PyTorch of for your lean, for your fast, for your MLP, that's a multi-layer perceptron, whatever. So you can do that here to load the data set, get the batch size, the block size, the training data, right? And these are all of these for the first forward pass, actually, for the first forward pass. Then we look at some randomly selected indices. We also look at the first 10 X element and first 10 Y element. You see that the X is shifted to the left, a bit to the right, most likely to the left. And so when goes in, the output is this. When it goes in, the output is this. When this goes in, the output is this. So this is all of the things that are going to the training process. The simple initialization of models. Let's keep all of that. We can always go through this notebook to look at what's going on here. So now that we have all of that, we can move our model into the CPU. We have save our model, move it to the CPU, we compile. So we save it into the CUDA, not CPU. CPU or CUDA, depending on what instance you're running on your Google Colab or wherever you want to train it. So you check your runtime and see what is available for you. Right. So we see that there's an embedding layer, there is the position embedding, there's a dropout, then there's like how it is there are 6 layers of this block, 6 layers of the layer norm, causal self-attention, the feed forward, the dropout, layer norm, that. So we see all of this in repeat. Then the output layer, the linear layer that gives you the output, the text outputs. So we're going to break down all of this into smaller chunks. The first thing is tokenization, which we've already talked about. So you have a sentence, we break it, split it if needed, and get their IDs. So we have these numbers. This is of the shape, batch size by sequence length. So we know this is going to be a matrix. Actually, even though this just looks like a vector ball, we have a batch size of 64 by or 16 by the sequence length, which we chose at 500. I think we chose the sequence length at 512. Let me not go back again. Choose sequence length at 512. So when you convert those strings into numeric values, each which represents a word or a subword, right? And we go on. Message. Okay. So then we have the embedding layer. There are two, there's not two ways. There is the embedded specific layer in PyTorch. If you're familiar with PyTorch, right, this is going to convert our input into an embedding vector. This allows us to understand a rich amount of information about input sequence and semantic meaning. I think I've explained this as the embedding layer we trained alongside. So this way to be initialized randomly, like Gaussian distribution from 0 to 1. Right? And they'll be learned during training. So this is how to initialize an embed. If you're familiar with PyTorch, you should understand what this is. And I mean by vocabulary size by the embedding space, which was 516 in our case. So this is how it will be. We have our tokens. Then there's like a search in the embedding matrix. So we are now going to get a batch size by sequence length by embedding dimension. Embedding dimension is 516. Sequence length is the 512 or whatever. Then multiplied by the batch size or times the batch size, which was 16. So we move on to the positional encoding. Remember from the paper, I told you that there was a new innovation. The first paper or the first GPT paper or the actual GPT model, GPT-2 model, learned the position encodings, right? So these are not embedding layer, just like this one, which is by block size, which is the shape block size by number of embeddings. So okay, so we see that this is one way to do that in a very simple way. We also found out that, okay, if you calculate these positional embeddings instead, right? It gives you the same level of accuracy. So instead of that, we can now use the touch.sign and touch.cosine to create our own embeddings, right? This is a class, and this is how this is how it is done in PyTorch. You inherit from the NND touch.model library, and you need to, should I go back to teaching PyTorch? Please, I don't know if you know this, but I hope you know it. I hope you are familiar with PyTorch and what all of this is. Okay, did I get a message? Okay. All right, so we know what the forward method does. The forward methods, it takes the X, that means the input or whatever is gotten from the input, and spits out the output. So that's what just the forward method does. So we are adding it with what X is going to give you now is going to be X, the embedding plus the positional embedding. So that's what is just being done here. So remember, we get the embeddings, then we add them with their positional. So you see that I've forgotten what it's called, but line by line, or I think it's broadcasting something. I've forgotten the terminology that it's called, but each embedding value is going to be added with a positional encoding value to get another matrix of the same size with the embedding matrix. So now this is the meat of the model, the scale dot attention mechanism. Right, first, like I said, the embedding size and the number of heads should be divisible without remainder. That's what the assertion is for. So whatever you set for your embedding layer and number of heads should be divisible and should not give you a remainder, so that it can be equally split up. You get the linear model for the projections. This is the first one that takes in your embeddings to get your matrices that will be used for projections. And we have the dropout for the residual and attention. We are setting some class attributes, instance attributes here. And this is the forward where the actual computation is done. We get the sizes, batch size, sequence length, and embedding dimensionality. Then we calculate our Q, K, and V, right, with the X, right? And we now do all of their rearrangements, right? So we are doing all of this we're dividing these to get what was it called? The number of heads. You see there's self.end.head. So that's where the splitting is done to get each of the keys that we use to do the multi-head attention. So I'm not familiar with this Flash, but it's something about optimization actually. So it's about CUDA kernels and for speeding up your matrix multiplications. And so I'm not really familiar with that. But if you do, you can always help out your guys. So that's about the attention mechanism. It's just a group of matrix multiplications, getting your linear models. That means there are weights here that are going to be learned. So then you now do the whole matrix multiplications, right? This is where all of it is done, right? This is where, so we're going to that. The first key component, the Q times K dot transpose. So remember, let me get to my slides again. Where is it? So Q times K matrix multiplication. Then there's a scaling. There's a softmax. So this is what is done. That's what is happening here. There's a new convention in Python, not really new, but the art is also the same thing as the matrix multiplication. Times 1 over the square root of the size of K. Remember, even the why they decided to use square root of K is in the paper. So you can look to the paper to find out why they use the square root of the dimension of K instead. So that's the first. The second one is the masking. Remember, you don't want to look ahead, right? Looking ahead will be cheating. So we mask out, depending on where we are in the pass, we mask out when you say float to minus infinity, it means that you're just like Xing those values out. Like minus infinity is the smallest value you can get. So setting those values to minus infinity is that we are just putting them into a very, very small value. So it don't really matter, right? So that's where the masking is done. And then the softmax, these are all touch methods. If you are familiar with touch, you can check out their documentation, PyTorch documentation. Sorry if you don't understand most of this, but these are what your researchers and the builders of GPT-4, GPT-3, this is how they went through. Some of them do. Well, that's why there's a lot of code that they do. But yeah, you are welcome to check out the touch documentation. You see the attention mechanisms. You see uh, the anti-convolution. We don't care about convolution. The linear method. These are just so there's a weight that is learning. There is also the loss functions, distance, and all of that. So there's also the typical touch.nm. Where is that? Yeah, so you can check the denormalization, recurrent transformer, and all of that. These are where you can look at what all of those particular terms mean. Dropouts. I hope you know what that is. The embedding layers, with just a simple lookup table that stores embedding. So this is not actually magic. They are there. You can always read them up. And like I said, the embeddings, they just initialize in this is what the normal distribution is from 0 to 1. So at initialization of this model, all of them are initialized in normal distribution randomly. Then they are learned. So and finally we get to this is where we compute the final attention scores, softmax of our attention scores. And so the attention score is multiplied with the values, and that's how we get our final output of the member of this part So if you look at the initial diagram, you see that there's a concatenation here. So all of those heads are concatenated, like I explained in the slides. All of those are now concatenated together to one whole large matrix and sent out to another linear unit. And we see also there's a residual. So sometimes if you're familiar with residual network, is skip connection. Sometimes the model might say, okay, there's no need for computing width here, it might overfit and stuff like that. It's based on the ResNet model. If you're familiar with the ResNet model in computer vision, you should know what the skip connection is. So this is me explaining what all this QKV. So all of this code here is all of this here, right? All of this here. Mask mode, the soft mask, causal mask, and the scale and the matrix multiplication. So please do try to read this notebook when you do have the time, and also check out Kapati's courses on building GPT from scratch if you really want to know your work okay, I see some. There are these questions. Why is it essential to neglect the bias? Okay, I see Good has asked some really nice questions too. So when it's not, you can also read the paper, but what I feel is that the bias is not doing anything, it's not adding anything, it's not subtracting anything to it. So why are you calculating it in the first place? Right? The bias in the linear regression was just to help you, right? Without the bias, like as if your linear regression is going to start from the origin. If you remember linear regression, right? They are learning some weights and you have some X. Without the bias, the line will always start from the origin. So with the bias, we are able to shift away from the origin up or down, right? So there's no need for that in this case because it's just giving you more weight to think about than expected. But you can always search, right? That's what I think. But you can always search online for that, why they don't use the bias in these transformer models, right? So where are we? Where are we? All right. So the initialization we are setting up I think this is for learning rate decay, stuff like that. So our weights, how learning rate decay. So some of all of these are to help our model training, right? Instead of having stuff like overshooting gradients. And you can always look up what this means, right? This is very, very handy stuff, right? So we initialize our optimizer, our checkpoints none, and we start. Okay, an option for you to compile. Compilation, touch.compile is a new like method brought out in Touch 2.0. And before Touch 2.0, we just build our model and no, these people for this, yeah, it's for this class. So before Touch 2.0, we didn't have the compiling ability, right? You just build your model and start like the training actually, right? But in I think from Touch 2.0 and above, there's the ability to compile. And what that helped do was like optimize, remove some unnecessary thing. Like also in TensorFlow, there's a compile. It came in, I think it has been there from TensorFlow from the beginning, but I think Touch brought this up newly, right? They found out that it will help optimize the models, right? There's a significant difference actually. You can check out their documentation for why the touch the compile is there. So now we create our loss function, we estimate our loss function, and we our learning rate create our learning rate scheduler, and we start the training loop, and we are not going to do that here. And so we get some outputs. Just want to like not take much of our time here. Please, if you do have a question, you can drop it in the chat also. And yeah, so we see that after the training, we're able to do some generation. So they crown me in this crown, golden crown, commandos, few revenues, and movables. This looks how I put it, this looks Shakespearean, right? So yeah, I think that's all for this. And should I share? No, I'll most likely share with Tamoye before I share with you. So yeah, that's it for today in the attention mechanism. So yeah. If there are no questions, I will end the session for today. But if you do have a question, drop it in the chat. I can just have like 2-3 minutes so you don't waste time here. Questions? Hope this link sent well. All right, so let me drop most of all of this in the chat so you can always have access to it. Okay. Share the notebook with how likely the slides too. Yeah. So thank you very much. Today we have covered like what I think an overview of what's going on in the attention and the GPT, all of that. And if there are no questions, I most likely call it a day. Thank you very much for joining today. All right.